Welcome back. In this video, I want to talk about formatting ordinary differential equations for use in MATLAB using ODE45. If you recall from last time, we talked through Euler's method. And just as a quick recap, Euler's method states that we can predict forward in time for any function y of t. All that we need is some initial conditions. So we need to know what y of 0 and y dot of 0 is, and how to get the derivative y dot of t. So if I know y of 0 and I know y dot of 0, I can now predict forward in time what y delta t is. And if I plug that in here and know how to get the derivative at any time t, I could then solve for y dot of t and thus get the next delta t later, and so on and so forth. So this allows me to predict forward in time and simulate things forward indefinitely. And that's exactly what ODE45 is doing in MATLAB. I've mentioned this in previous videos, but ODE45 isn't actually using Euler's method. It's using something known as ODE45, which is another numerical integration process. But the principles hold the same. It just needs initial conditions, and it needs a means of getting y dot at any time t. And so I want to talk today about how we can programmatically tell MATLAB how to get y dot of t. How can we tell MATLAB what the derivative would be so that it can run with this, it can predict forward in time. And the first thing you'll notice is that this formulation of Euler's method, and the same holds true for ODE45, is that it's a relationship of a single derivative. We have y of t and the first derivative y dot of t. However, many of the differential equations that we deal with in dynamics are second order differential equations. And theoretically, this could hold true for third order, fourth order, fifth order, sixth order, and so on and so forth differential equations, which mathematically are very plausible, but for the most part in dynamics, we deal with second order differential equations. So I want to illustrate this with a simple example. So in this example, let's suppose that we have a mass attached to a spring. So we'll say that this spring has a spring constant k, and the mass has a mass m, and the horizontal direction we'll define as x. Now let's suppose that this spring has a resting position xr, the r representing resting. Well, from Newton's second law, we know that the sum of forces acting on this mass is equal to the mass times its acceleration, a. If we assume that this mass only moves in the x direction and that the surface is frictionless, the sum of forces equals mass times acceleration will only be in the x direction. So the only force that we really need to take into consideration here is that due to the spring, which is defined as minus ks, where this lowercase s represents the amount of stretch in that spring. So how far has it been perturbed from its resting position? And since we're just looking at the x position and we're assuming this mass doesn't move in the vertical, we can say that the acceleration is just x double dot. So plugging these in, the sum of all forces would be minus k times the stretch, and the stretch we can define as x minus xr. And if you're unsure about whether it's xr minus x or x minus xr, it's always helpful to try some numbers. So if I say that the resting position is 1 and I pull it further to the right to some position of 2, I expect the force of the spring to be acting to the left, so a negative force. Well, if I plug in 2 for x and 1 for the resting length, 2 minus 1 is positive 1, multiply that by a negative k, that's indeed a negative force. If I had these flipped, it would say that it's a positive force, which doesn't make sense. It means if I pull it to the right, it's just going to speed up and keep going to the right. So it seems like our directionality here is correct, and this is going to equal our mass times acceleration, which we've defined as x double dot. If I rearrange things just by multiplying through by 1 over m, I'm left with x double dot is minus k over m times x minus xr. And this here is our second order differential equation. We have x double dot as it relates to x. And as I alluded to earlier, Euler's method, or ODE45, seems to only have this relationship between y and y dot, so a first order differential equation. And here I have a second order, I have x double dot and x. So I need a clever way of defining or introducing these differential equations to MATLAB that break it down into multiple first order equations. And the way that we're going to do that is with something known as state variables. So I'm going to define a state variable vector. And my state variable vector I'll always represent by this capital script S. And because I'm interested in predicting forward in time the position x, and my equation of motion is x double dot, I may want to choose my state variables to be something like x and x dot. Meaning, if I have my state vector at some given time t, so if I know x and x dot and wanted to take the derivative of it to get script s dot, that would represent x dot and x double dot. Well, this equation x double dot is exactly what I just solved for. So this is two first order differential equations that I could write out to describe this second order differential equation. Now, as I said earlier, in MATLAB, if we just know the initial conditions, so if we're given our state variable vector at t equal to 0, and we know how to get from s to s dot, well, s at t equal to 0 gives us our starting y of 0 and y dot of 0, which allows us to predict forward in time. We can plug that in, and as long as we know how to get s dot, as long as we know how to get this derivative, which is this arrow that I've circled here, we can now predict forward in time. So those are kind of our things that we need in MATLAB to use ODE45. We need initial conditions, and we need a means of getting from our state variable vector to the derivative of our state variable vector. So I'm going to start writing this out in terms of indices, very similar to how you do this in MATLAB. And so what I want to do is say, all right, my state variable vector dot index 1. So the first index of this vector that we've set up, that's x dot. And I want to represent or describe this equation in terms of s. Well, x dot is simply just x dot. We know what that is by our state vector. So this is just our state vector index 2. These two are exactly the same. Where it gets interesting and where we get to introduce our second order differential equation is s dot index 2 is x double dot. Well, x double dot we've described up here as being minus k over m times x. Well, x is represented by our state variable vector index 1 minus xr, assuming xr is a constant. In this here now we have first order differential equations. We have a relationship between s dot and s in two equations. So we have s dot 1 and s dot 2, which are represented as functions of s. So these are a first order differential equation, or a series of two first order differential equations. And this is programmatically what we're going to hand to MATLAB. It's basically a tool of saying, here's how you get from s to s dot. In our next video, we'll talk a bit about how to do this in MATLAB, how to programmatically do this with the same equation. But this is the first step for any time you're using ODE45, is to set up your state variable vector and describe how to get its derivative. Now, what we've done here with this simple example relies on just x. So there's only one second order differential equation, but in MATLAB, you could easily have multiple. You can imagine if the spring was moving in the x and y direction, maybe our state variable vector looks like x, x dot, y, and y dot. There's no rule that says that these state variable vectors have to all be derivatives of the same variable. You could have multiple variables in there. So we'll talk a bit next time about how to do this in MATLAB and how to hand this off to MATLAB so that it can predict forward in time. Thank you.